tutorial, we're going to look at how JPF is able to find the deadlock in a Dining Philosopher problem. In Dining Philosopher problem is where there are 5 or 6 philosophers sitting in a circular table, and there's 2 forks the sides of each philosopher, and they can only eat if they have both the forks with them. And either there is a possibility of deadlock or there is a possibility of starvation. So here in this program, it tries to simulate that scenario, especially the deadlock scenario. So we're assigning the number of philosophers here and the number of forks here. So as soon as we're initializing number of forks, and the philosopher each philosopher gets 2 forks, and then we start. So there's actually the shared fork between every philosopher, and when there's a start, so the first every philosopher tries to pick up the left fork, and then that's why we're having a synchronized block here on the left fork. And as soon as they get the left fork lock, here we are simulating through locks, and they try to pick the right fork. So if everybody tries to pick the left fork, there are some possible combinations of threads, the thread scheduling timings, in which the every philosopher would get into a deadlock situation, so nobody can eat. But if you run this application using normal Java, it is very hard to find the deadlock scenario out here. I can try to run it in Java. Um, so right click the application and run file. I give the number of input philosophers as 6. Click OK. So the program runs fine, and it completed successfully. Most often it's going to be working fine, but there's some particular combination of thread interleaving, the scheduling interleaving, for which this could definitely lead to a deadlock. I already tried to run it using JPF. All you need to do is the same thing, go to the DiningPhilosopher.jpf file, and then right click it and then click verify. But this is taking more than a minute, so in the interest of time, I am not running it again, but I can show you the output, what JPF produced. So here it clearly says it violated the not deadlock property, and all the 6 threads were blocked. And it also tells you the thread 1 owned locked this one, and it was blocked on this particular thing, and if you click it, it's going to take you to which particular line actually caused the deadlock here. So JPF tries to, it's the exact same philosophy what it uses for that random number, but here the number of combinations it needs to check is all the possible thread interleaving schedules, which is quite heavy. But as I said before, it uses recursive backtracking, so on and so forth. And if you look at the DiningPhilosopher.jpf here, here we have given the same target, Dining Philosopher. That's the program which will be invoked, model checked. And we have given the search strategy as BFS, breadth first search. If you, the code is available here. There is a lot of other search strategies as well. Depending on your exact need, you can pick the class that you exactly want. So that's it about the Dining Philosopher problem. Thanks for watching the video.